Okay, first, I want to talk about scalar and vector projection. If I've got two vectors, let's call them u and v, I can project v onto u. I could also project u onto v. To project v onto u, first I sketch or think of the vectors as having a common initial point. And then we go from the tip of vector v at a perpendicular to the vector u. Then this displacement here is the projection onto u of the vector v. It's just the displacement. Okay, so this is going to be a positive or negative number. Now there's also a vector projection. I'll sketch it in a minute. There are two cases, actually, I guess three. If v is perpendicular to u, then it's obvious that the perpendicular projection from the tip of v down to u is 0. You can also have v making an obtuse angle with the vector u, in which case we extend the line of u and project down here. And right here is the projection onto u of v. Now, this projection is not a vector. I'm using an arrow here to indicate the displacement in the sense of being either positive or negative. You could think of it as a vector, but not in the same space as the vectors u and v. You'd just be in a one-dimensional space, and I don't think that's something we need to worry about. Okay, so these are scalar projections, just numbers. This picture depicts a positive vector. In other words, just go over the picture. And over here, we have a negative. Okay, now I can draw the same pictures. You use almost the same notation. But now I want the vector from the initial common point of v and u over to this point. Okay, now this is a vector, so we're going to call it same notation, projection onto u of v. But this one has an arrow over it because it's a vector. Okay, this is not these are not both just magnitudes. The scalar projections aren't just magnitudes because a scalar projection can be negative. So neither one of these is really the magnitude of the vector projection. Although in the case where the angle between the vectors is acute, then the magnitude would equal scalar projection. In this case, magnitude of this vector would be the negative of the scalar projection. That is, in the case where the two vectors are obtuse, or the angle between the two vectors is obtuse. Not sure you can talk about obtuse vectors, vectors that don't understand what you say to them. I don't know. Okay, so I can draw this picture. Yep. I messed up because I'm about to draw the same picture. Okay, or a picture with u to the right. And v making an obtuse angle with u. And in this case, the vector projection would go from the common point of u and v in the negative direction. Okay, so this is the vector projection on U of V. In this case, make sure we got an arrow over that. It's kind of a small arrow, so we just made it bigger. Okay, well, how do you calculate the scalar and vector projections? Just taking this one picture as an example, I have between the projection line, the vector V, and the line of vector U, I have a right triangle. The angle between the vectors is theta. The length of the vector V is its magnitude. Then it follows from very simple right angle trigonometry. One of the first things you learn about the sines and cosines is that this scalar projection is equal to the magnitude of V times the cosine of theta. Now, in the case of V making an obtuse angle with U, you maybe want to think of this as your x-axis here along the vector U, circular model. So you have the obtuse angle, and the projection is the x component, which is again the magnitude of V times the cosine of U. If we want the vector projection, we have to do just a little bit of work. Again, I'll sketch V. I'll sketch the vector U and the projection line. And then I'm going to sketch a unit vector in the direction of U. So this vector would be the vector U over the magnitude of U. Now, the unit vector might be smaller than the vector projection, it might be bigger. If it's smaller than the vector projection, then the vector projection is going to be greater than 1. If it's bigger than the vector projection, then the vector projection is going to have a magnitude less than 1. Okay. In any case, then the vector projection on U of V equals the scalar projection multiplied by the unit vector. I had to squeeze that in. It's just U over magnitude of U. Projection onto U of V times U over the magnitude of U. Obviously, this is a unit vector. If you multiply it by the magnitude or by the projection, you're going to get the vector projection. Now, the last thing about that is, here's the scalar projection. Or it's getting a little bit cluttered. So I'm going to use just a little bit of this board. So the scalar projection of V onto U equals magnitude of V cosine theta. It should be obvious. Your angle is theta. Note that dot product is defined to be magnitude of U times the magnitude of V times the cosine of theta. And right here, this expression magnitude of V cosine theta is right here in the definition of U dot V. Follows then that V cosine theta, and that would be magnitude of V cosine theta, equals U dot V divided by the magnitude of U. Well, magnitude of V cosine theta is the projection onto U of V. So this is the scalar projection onto U of V. That equals U dot V over magnitude of U. And then the vector projection onto U of V equals U dot V over magnitude of U, which is how big this projection is, and also positive or negative according to whether the angle is greater than or less than 90 degrees, acute or obtuse. So that's the magnitude of this thing. And remember that the vector projection is just the magnitude multiplied by the unit vector U over magnitude of U. So if we multiply this magnitude with the scalar projection by U over magnitude of U, we have it. There's the vector projection. It's very important quantity, very important calculation, very important concept. Now, typically your textbook will then not bother much with this formula here that makes perfect sense. I mean, U dot V over magnitude of U is just magnitude of U, magnitude of V cosine theta over magnitude of U, which is magnitude of V cosine theta, which is your scalar projection. Again, there's your scalar projection. So U dot V over magnitude of U, there it is. But then we've got another magnitude of U here, so it tells you magnitude of U squared. And this is just a number multiplied by the vector U. In my opinion, this is a nice, elegant formula that disguises what's really going on. And I kind of advise you to think of it this way and write it down this way, so you don't have to rely on memorizing a formula where you don't really remember, is that a square, is that a cube, is it 3/2 power? Because those things pop up all the time. I would not memorize this formula without knowing where it comes from. That gives you much greater insight into what's going on with the dot product. Well, that's essentially what you need to know about scalar and vector projection. Now you're going to see how we use it. We're going to make fairly extensive use of it in most of the course. But we first have to be able to calculate it, understand it, manipulate it, and so forth. So if you understand this nucleus, then you're ready to do scalar and vector projections. Now, one thing we can do with this, if you want, looking for my chalk, okay, if you quick numbers, will I give myself a little more room? Another thing that comes out of this, if I've got V and I've got U, and I know the vector projection onto U of the vector V, then how can I calculate this vector component of V perpendicular to U? Here's the picture again. Here's the component of V in the direction of U. Then I'm going to draw here the component of V perpendicular to U. It's often important to be able to find the components of a vector parallel and perpendicular to another vector. You'll see that quite soon. Well, this component is the projection onto U of V. So first of all, V is equal to the parallel component plus the perpendicular component. In other words, if I add this vector to this, put them head to tail, they're going to give you this vector because, of course, the component of V perpendicular to U is the same here as it is here. This line is parallel to U. And you can see clearly that this vector plus this vector equals the vector V. So the perpendicular component equals V minus parallel component. It's simple, V equals this plus this. So this equals this minus this. Simple equation. And now we can draw what might be an important picture. Here's V. Here's U. Here's the vector projection. Onto U of V. And put it here. This is a vector V minus the projection on U of V. And it's pretty clear. If I add this to this, if I add the projection onto U of V, the V minus the projection onto U of V, what am I going to get? I'm going to get V. Picture shows you this plus this equals vector V. And everything makes sense. Now, projection onto U of V is what again? It's U dot V over the magnitude of U. If you think, again, the definition of U dot V, magnitude of U, cosine of theta. If you divide out the magnitude of U, you're going to be left with the magnitude of V cosine theta, which is the projection, scalar projection. And that's multiplied by U over the magnitude of U. So that the perpendicular component is this. And I wouldn't memorize this as a formula. I wouldn't memorize this as a formula. I would recommend understanding what the projection is and why this is the formula for vector from here to here in the direction of U, magnitude equal to this side of this triangle. Okay, that's all I'm going to say about scalar and vector projections for now, but we're going to be using them, so I do recommend that you understand this as thoroughly as possible. One application, we've already talked about something moving along a curve in space. You can get a unit tangent vector. You can project the acceleration vector onto the unit tangent vector to get the acceleration in the direction of motion. Then you want the acceleration perpendicular to the direction of motion. Now, there are two ways to get that. One is to subtract the vector projection from the vector projection of the acceleration vector in the direction of motion that is parallel to the unit tangent vector. Subtract that from the acceleration, and you get the acceleration perpendicular to the direction of motion, which is a centripetal acceleration, at least instantaneously relative to an osculating curve, and we'll develop that idea a little more thoroughly very soon.